Even though it's
Oh my gosh. I didn't know you were that strong.
Other questions.
Yeah, but I don't even care. I slow right, but my it's past the worst.
Yeah.
Yeah, no, same as last fall.
It was always fun. And then he said, I was so trying to who's the art? I know that not as shorter.
Which means
Are we doing it?
it's the same temperature. Then that means
It's the same.
Yeah.
Okay. We'll be wrapping up circular motion with this question and then moving on to springs and work. All right, so last time we ended on this question. So the diagram again, we already figured out that the car, assuming that the car is going into the board, that it is turning left. And so say this is some angle theta. So yes, the question is which of these is the correct free body diagram and acceleration? Let me just I'll give you a few seconds to think, and then I'll ask you. Then we'll discuss. Anyone need more time? All right. Any of you? Okay. All right. Variety of answers. Slight majority for E. E is indeed the correct answer. So let's go over why that is. So we know what a bank curve is, but the question is, what do we mean by the design speed for the curve? So if the car is traveling at the design speed for the curve, what that means is that it doesn't need the help of friction to take that curve. So in that case, there would only be the normal force and the force of gravity acting on the power. So at design speed, the free body diagram would be force of gravity, normal force. So this would be the angle theta, and it is going around in a horizontal circle, right? So which way would the acceleration be? Yep, it will be horizontally to the left here. So yeah, so the acceleration would be like this. All right. So this is at design speed. But if in this case we have a car going too slow, right? So in that case, what's likely to happen? Will the car slide? Does it want to slide up the slope or down the slope? Down the slope if it's going too slow, right? Too slow, yes. So when you're below design speed, you still have mg, you still have fn. But since you're in danger of slipping down the slope, the force of friction will point up the slope, and it'll be a force of static friction, because even though the car is moving, the tires are gripping the road, and there's no sliding going on between the tires and the road. Yep, acceleration is still horizontal. So for this sort of diagram, when you're analyzing it, you would choose your axes so that the acceleration lies along one axis. So in this case, I would probably choose like this is y, this is x, and then I figure out well, I know that this is theta, and this is also theta. And then I write my equations. So in the x direction, what do I have? I have Fn sine theta minus FSF cosine theta. Those are the only two forces with horizontal components. And so then that combination must be equal to m, and this is centripetal acceleration, so it'll be MAC. And then in the y direction, I have f net y equals MAY. And so now that would be Fn cosine theta plus FSF sine theta minus mg equals 0, because it's not accelerating in the y direction. And there you go. This would be these would be the two equations I need, assuming that I have the mass and the angle and the speed. How does the speed come in? Well, because this is centripetal acceleration, this is secretly mv squared over r. So if I have the mass, the angle, and the speed, and the radius, then my unknowns are just Fn and FSF. And so I have two unknowns and two equations, and I can solve. At this point, we haven't said that it's on the verge of slipping or anything like that. So I cannot assume that the static friction is its max value, right? So I would need to solve these equations to get the force of static friction and also the normal force. If I additionally say, oh, this car is on the verge of slipping, then you can assume FSF equals μs times Fn. That will simplify things a lot. But yeah, even without that, if you have enough information, you can solve this. It's very similar to the problem you did, or some of you saw at least, maybe I don't think anyone completed it, on Friday with the spinning cone. Yeah, very similar set of forces. Yes.
I would love a little bit of clarification why the acceleration is horizontal and not tilted that way.
Okay, because if you just look at the car, subtract away what it is moving on, then what do you see? You just see a car going in a horizontal circle.
Sure.
And so if it was at a constant speed, then uniform circular motion, the acceleration would be
I see, so if it was going like this, then the acceleration would be inward to the center, but it's actually going around.
in a horizontal circle. Yeah, yes. Other question? Okay. All right, so then we will move on. So our next topic is about springs. And so springs, or something like springs, come up a lot. So what we'll say is that an ideal spring is massless and obeys Hooke's law. And so the idea here is that if you have a spring with some natural unstretched length L0, all right, so for example, one of these, right, unstretched length, and then you can stretch it, right, or compress it. This spring doesn't do compression very well, but you can stretch it, right? So you can stretch it, a new length. And then we can define S as the magnitude of that difference, right? How much it has been stretched or compressed. Well, in that case, what we say Hooke's law is right. So let's be clear what these are. This is the magnitude of the spring force or tension in the spring. S is that quantity defined there. Under the stretch. And K is the spring constant. Sometimes it's called the force constant, but that's too vague, so I prefer spring constant. Yes.
This is spring constant, also known as units.
Oh, let's check. So, K here would be FST over S. So the units would be, what do you think? Say it louder.
It's newtons over meters.
Yep, that's right. Yeah, units of the spring constant would be newtons over meters. Yeah, it's basically telling you how much force do you need to apply to stretch the spring by so many meters. Other questions?
Wouldn't that assume that every string could be the same amount?
Well, no, different springs would have different string constants, yeah. Yes,
You said tension in the spring instead of on the spring, is that like a distinction?
no, I mean, once you connect the string to something, then you talk about like, oh, the force of the spring on something, or the force of that something on the spring. But when you use the third law, those would have the same magnitude. Other questions? So what Hooke's law is saying is that the more you stretch it, the more force you need, right? Yeah. Let's see, is there anything want to mention here? We talked about the units. Oh, okay. Don't write what I'm going to say down just yet, listen to me, okay? You will see places that say, oh, force of spring is like minus kx. This is, it's not wrong, but it's not the best notation. The reason is like minus signs, as we know, tend to depend upon how you set up your coordinate system. So really this is, oh, x component of the force of the spring is minus kx. Okay, if you're just talking about the magnitude, then you don't need a minus sign.
So you're saying you would calculate the magnitude and then based off of your coordinate systems, the asymptotic direction you define which is not.
Exactly. Yes. Okay. All right, let's do a couple of quick spring questions. Oh, question, yes.
Would the same spring have a different K for if it's compressed versus if it's stretched?
Oh.
That'll be dependent on material.
Very good question. In reality, yes, springs can react differently to compression versus stretching. In ideal springs, though, it's like that. So that's what we'll imagine in this course. But you're correct that in reality, people talk about compressive strength and tensile strength and stuff like that. Yeah. Like bones, for example, it's like how much they can resist a stretching force versus a compressive force. All right. So yes, okay. Look down screen. First, very quick one. Okay, anyone need more time? Okay. Mostly for either A or D, remember to keep track of your units. So we're doing force of the spring divided by how much is being stretched. So this would be 6 newtons over 0.3 meters. Right, and so it would be 20 newtons per meter. Meters there, yeah. What about Anyone need more time? Bit more time. Okay, get ready and vote. Okay, all right, so people have narrowed it down to either A or B. That's good. Go ahead and discuss.
I just think the parents would say. So that they change the same. I mean, maybe it's about. Yeah, exactly. I don't, I mean, I don't really. Oh, yeah. So then don't.
Oh, yeah.
There's two.
It's probably the next question.
But here it's.
Yeah, there was a little bit of.
That's the other.
I mean,
I'm not sure.
say that
What, that's-
range as
Is it plus?
6 meters attached or 6 meters.
No, I think it also, that means the bottom spring goes down on that side. I feel like the first one also has the. But in the
The math is not bad.
If you.
I don't know why that's.
But it means zero not first thing.
I don't.
Yes. Okay, you guys are right.
Oh.
Okay. All right. Get ready. Okay. Still torn between A and B, but leaning towards B, and B is correct. So let's see why. Well, first let's actually do the demo. So if so I have two springs, and they're fairly close in K value. And so we can see the first spring, I hang it here, and okay, so the end point is around the 6.6 mark. Not really sure what units these are. And it stretches to, what is this, 5.2-ish. So 6.6 to and 5.2, so 1.4, okay. So now if I, yes. Look in the other one. So now this endpoint is at about about four, yeah,
You have a distance that's not spring, right?
sorry.
In the middle, you have a distance that's not spring.
Ah, that's true. But we're interested in how much the endpoint moves. So, yeah,
Whoa.
right, you can see it clearly stretches the combined amount. Right. So what's going on? So the idea here is that when they're placed like this, we're told that by design they have the same spring constant. But when they're placed like this, whatever mass I put here, whatever weight I put here, they both have the same tension in them, right? And to hold this stationary, the tension in this spring must be 6 newtons. But then to hold this spring stationary, the tension in this must be 6 newtons. So each of them experiences 6 newtons force. Each of them stretches 20 centimeters. Total stretch is 40 centimeters. Yes.
What if I combine those two springs together? What would it be to that? I mean, if the two, what's the difference between separate two strings and one string?
So basically, it's tempting to think that the spring constant only depends on the material, and that when you put these two together, they should just become one big spring of 30 newtons per meter. But the spring constant also depends on the length of the spring. And so when you combine them, the effective spring constant changes. And in fact, we could come up with a formula for that. I'll use the whiteboard.
Yeah.
That's 200.
I mean, if you look at this as one system.
You should just skip this class. Just watch it.
I know it was the same.
Alright, so we would have F1 equals K1 S1. F2 equals K2 S2. And when we put them in series like this, we say that we're putting the springs in series. K1 to K2, we put something here. Then what we know is that the S effective is going to be S1 plus S2. But that is going to be F1 over K1 plus F2 over K2. And so if I'm replacing this with a single effective spring, I would have F over K effective. But in this case, what we see is that, F equals F1 equals F2. So I can cancel those out. And so what I get is, 1 over K effective equals 1 over K1 plus 1 over K2. This is for springs in parallel. No, not parallel, series, sorry. Take a moment to absorb that. Ask any questions. Okay.
How do we know that all the forces are like equal?
So if I draw the free body diagram of this block, I'll have mg and force of spring 2, right? Which is really force of the spring 2 on the block, right? And when it's reached equilibrium, the acceleration is 0. So we know that these two forces would be equal in height. If I draw the free body diagram for spring 2, I have force of block on spring 2 and force of spring 1 on spring 2. By Newton's third law, I know that these two forces are equal. And again, the acceleration is 0, so that these two forces must be equal. So that's how I. Yes.
This means this spring to have 12 newtons of stretch.
No. Well,
Because it's what 6 newtons were act by.
oh, I see what you mean. Right.
Force and the energy also.
Yeah, but I mean, how do we define tension in a spring? Right, at the end, when you stretch a spring, right, and you hold it stationary,
Yeah.
it's not going anywhere, so the net force on it has to be 0. Right, but that's not a useful description. So in other words, we say like, how much is the force on one end? That is your tension in the spring.
Only one end?
Well, because if you try to do total force, it would just be 0 all the time, no matter how it's stretched. Other questions? Alright, you look like you're on the verge of a question.
Yeah, I don't know how to word it. It's like what if it's compressing? Like what if it's actively being compressed? Like what if there's an acceleration?
Wait. Compression or acceleration? Which one?
Like if you like launch a block into two springs that are in series,
Okay.
the acceleration will be the same through the system, so all the forces would also be the same.
Oh, yes. Yes. I think so, yeah. That's an interesting question, yeah. But yeah, no, the tension should be transmitted throughout, yeah. Oh, was it? No, okay, sorry. Yes,
When we like look at a spring, like as like physicists, are we treating it as like one entity, or are we treating it as, cause like you could have one side like accelerating / like moving while the other side stays stationary, so like.
For this course at least, we will be treating it as one entity. Yeah, you're like, definitely, yes, you're right, it does become more complicated when, there are situations when you have one end of the spring is moving and the other end is not. Some of you might have seen that famous Veritasium video where he drops a slinky in slow motion, and you can see that like the bottom end of the slinky stays where it is as the top one falls down. And so what's interesting then is, when there's a change in the force on one end, how long does it take the other end to know? Right? And that is a question about like the transfer of physical information. That's a waves question, which we will postpone to the waves course. All right. So that's we did 2 springs in series. You could also do them in parallel. If you do them in parallel, then they are sharing the burden, and so they're splitting the 6 newtons between them. Each of them is only taking care of 3 newtons, and so the overall stretch should be less. Oh, I put a 1 kilogram mass this time. That's why it looked different. This was the 500. Yeah, so much less. And it makes sense that the string constant would depend on the length, because what the material determines is how stretchy each of the individual interatomic bonds is, right? But then how much does the spring as a whole stretch? That would be that stretchiness times the number of bonds, which is determined by the length of the spring. Right, and so the longer your spring is, the more number of bonds you have that can each stretch a little bit, and so the bigger your overall stretch would be. All right. Okay, so talk about springs. So now let's talk about work. Let's see. Yes. Okay, I'll put up the screen. So, the idea of work, unfortunately, it's one of those cases where like we have common language use and then we have the physics use, and they're not quite the same, right? So this is a lead brick. Some of you have like picked it up and know it's actually quite heavy. So if I'm holding it like this, at least in common language, I'm doing work, is it's like, it takes some effort to hold it like this. But in physics term, if I'm not moving it around, I'm not really doing work to it. So what is the physics definition of work? Okay, so work. All right, what's going on here? We're talking about the work done by a force in taking a system from an initial state to a final state, or initial position to a final position. Right, so. Let me clarify also, because I know in thermodynamics, depending upon how you set up things, you might talk about the work done by a system, the work done on a system. Here we're talking about the work done on a system in taking the system from an initial position to final. So our friend, the dot product, makes a return, right? You might ask, what's this dr vector here? The dr vector, well, what's the r vector? What do we call this? This is the position vector, yes. And we know this position vector is just like xi hat plus yj hat. And so the dr vector is going to be dxi hat plus dyj hat plus dz. Right, so it's talking about the displacement. It's talking about a small displacement. And so the idea is that if you have some object that's being moved along a path, let's say from here to here, and there's some force acting on the object, what you do is you chop up this path into tiny, tiny pieces. So that even if it's a curved path, a tiny piece is short enough to be almost straight. Okay, and so each little piece here would define a small displacement vector dr. And then what you would do is you'd be, oh, when it's at this position, what is the force vector? Maybe when it's at this position, the force is like in this direction. And so you would do the dot product between that force and that tiny displacement. This might not be the net force, this might be just a single force acting on the object. So yeah, you would do the dot product, and that would give you a scalar quantity. And then you'd repeat it for the next step, and repeat it for the next step, and so on and so forth. Add those all up. That's what this integral means. This curly symbol here is really stretched out S for sum. It's a sum of like infinitely small little pieces. All right. But we know that a lot of you are just getting used to integrals, so we won't ask you to do that many. But there are two things we can keep in mind. One is, if I give you a graph of how the force varies with position, we know that graphically integrals correspond to what? Area under the curve, exactly. So then even if you have a varying force, you can still sort of calculate the area under the curve as long as the curve is not too complicated. And so you can figure out the work from that. The other case is if the force is constant. This is a special case. If F is constant, then one thing you'll learn when studying integrals is that if you have a constant, you can pull it out of your integral. So if your f does not depend on the position, doesn't change over the path, then it becomes f dot this integral. Like this way. Well, okay, I'll go down here, right? And so integral dr is just going to be r, evaluated at the final and initial positions. And so then this becomes f dot r final minus r initial, which is f dot the displacement or the change in r. So you can use the simplified formula, but only if the force is constant. Yes,
The delta R still being a vector?
yes, delta r still being a vector.
Would you need to not calculate a magnitude? Like, are we using this vector formula? I don't understand why it's a vector and not the magnitude of this distance. Like, why do we not take the distance formula?
Remember that this is a dot product. Right, so it's a dot product between two vectors that will give you a scalar.
Okay.
And if you want, there's one way of doing the dot product is what? Magnitude of the first vector times magnitude of the second
Yes.
times the angle between them. Right, so you do need to account for this angle because not all the force is helping the displacement. Basically, what the dot product is seeing is like how much of the force is along the displacement, and that is telling you the work done by that force. Yes.
Is that assuming that the work done, if there would be a straight line, would be equal?
Oh, if right, yes. So in this case, when the force is constant, yes, the work done would be the same regardless of whether you took this curved path or whether you took a straight line path. Yeah. Other questions? Okay. So why is work a useful concept? It's because we can relate it to kinetic energy. Right, I'm going to erase some of this part. Is that okay? So I'm going to show you let's see, how should I put this? Yeah, it's not a proof, because we'll make mathematicians roll in their graves. But it's a sort of indication of where this idea comes from. Okay, so we have W equals F dot dr. If so then we puts it in the total work. So then that would be integral F net dot dr. But by the second law, F net is equal to Mn, yeah. Right, we're assuming mass is constant. But what is acceleration? What's the definition of acceleration? Well, the formula for acceleration. Change in velocity with change in time. So I can write this as now this is, oh yes,
Why didn't we pull M out, like?
Oh, we can, yeah,
Okay, we
it
can.
doesn't matter whether you keep it in or pull it out. But already in going to this step, we have to assume that M is constant. Okay, okay, and now this is the step that makes mathematicians mad.
Still a dot product.
Still a dot product. Right, I just shifted the dt over. So what is dr dt? Well, just velocity. Yeah, right. Dr dt, change in position over change in time, so that's just velocity. And so that is equal to integral the dv dot with v. Okay, and so we have m v dot dv. And so then this becomes m v squared over 2. And so this becomes 1/2 m v final squared minus 1/2 m v initial squared. And what we started with was total work. So that is the work energy theorem. Is the total work or net work done on a system is equal to the change in kinetic energy, where K is 1/2 mv squared.
So we have integrals. We usually we have like some the something at the end. Where is
Well, I mean, initially that was dr, and then we switched it to dv.
that's a vector?
Yes, it is a vector, yes.
Why can we put the DT under the DR?
Yeah, that's the part I'm not gonna justify. We're physicists, that's what we're gonna say.
That's so funny.
Yes.
But like, are we just like, we're just like switching from taking a little bit of one thing to like taking a little bit of another thing, like over time?
Yes, exactly, yeah.
In this step, are we just gonna treat the dot product like it's regular scale multiplication? And that you integrate the same.
Good question. Well, actually, you can expand this out. And so then this would be m, and then this would be vx dvx plus vy dvy plus vz dvz. Right? So then each of these would become like vx squared over 2 plus vy squared over 2 plus vz squared over 2. That's the same as just v squared over 2. Yes.
So for these velocity initial and finals, we would take the like x velocity and the y velocity and we would do them separately?
Well, I mean, in the end, it turns out it doesn't matter. You just need to take the overall velocity magnitude squared. Yeah.
So when we do that dot product that you just did, is that essentially splitting it into 3 different intervals where we
Yeah.
have all the arms with respect to their
Yeah, one is respect to dvx, one is respect to dv.
And you
But they're all from
combine
initial
them
to
all,
final.
and we combine them all.
Yeah. After.
And then we take the integral, it's no longer a vector, it's just a scalar?
That is correct. Well, actually, once you do the dot product, it is the same.
Okay.
Oh, actually, I can't remember that.
Yeah.
That's really funny.
All right. Any other questions? Yeah.
Just run bounds, like.
Oh, it's still from the initial position to the final position? Well, actually, in this case, from the initial velocity to the final velocity. So that's what changes when we switch over what is our d quantity. So here it was from position initial to position final. now it's become position velocity initial to velocity final. But those happen at the same moments, so there's not really a change.
If you're integrating and you do like change the interval, there'll be that time the interval would have to like. Hold out after that.
Yeah, so you're basically sort of changing your integration variable, and so you have to change your balance. Okay, I guess that's time.
It's the same. Like basically, like, something. Which I never.